Okay, welcome in this recording for chapter 4 regarding the intercept. The intercept is a method which will help you to determine your position during celestial bodies. Okay, so I start with a small introduction. So we all know that when we take the height of a celestial body, that we will need a sextant. Okay, and if we combine this height that we get from our sextant, and we can determine at the same time the time of observation, this is nothing else than checking the time on your chronometer, which will indicate universal time. If you combine these two elements, the height, which is hv, that you will get the true altitude, and you combine that with the time of observation, meaning that you have watched your chronometer when doing the observation. If you combine these, you can determine your position. Okay. Well, first, some history. How was this method discovered? Well, the first basic of this concept of the intercept method was based on Captain Sumner's observations. In 1837, he was sailing somewhere along the Irish coast, and unfortunately, he had been unable to take a fix. A fix is a position fix for a couple of days due to bad weather. There were too much clouds, and he couldn't take a clear shot, or he couldn't get a clear view from the sky, so it was unable to measure the altitudes of the celestial bodies. Okay, but then at a certain moment, he did manage to take a shot from the sun, and he noted the time on his chronometer. Okay, his only worry was that his dead reckoning position, on which he was basing, his estimated position was based, his dead reckoning position. He was scared that there was an error on the latitude. Okay, so what did he do? With the same height that he obtained from his observation, the shot from the sun, the only shot that he could take, what did he do? He calculated his position on 3 times, 3 different occasions, 3 different situations. Okay, he did it once with his dead reckoning latitude, and then additionally he did 2 more calculations with a latitude of 10 minutes more to the north and 20 minutes more to the north. Okay, and he discovered a very special thing. What did he discover? He discovered that the 2 positions that he obtained, the 3 positions that he obtained, they were all on the same line. Okay, and this line is the line that we call now, it's the red one that you see here, that is what we call now a line of position. Okay, so he discovered that his 3 positions were on the same line, so he realized that any ship seeing the sun, because he did an observation of the sun, at the same altitude, because he only had 1 observation from his sextant, he had 1 observation, okay, but he used 3 different latitudes. Okay, so he said, okay, the positions that I get from this calculation, they are all on the same line. So if a ship is here, or a ship is here, or a ship is there, they are both sighting the sun under the same height, because he only had 1 observation from his sextant. Okay, voila. So he said all the ships seeing the celestial body, in this case the sun, on the same height, they must be on that line of position. Okay, well, this I will explain to you later. Okay, he also discovered another thing. He also discovered that if he would have made errors in the altitude with his sextant, so these are errors that he could have made himself, he saw that they could be corrected. Okay, and how could they be corrected? They could be corrected by moving the line of position towards, that is in that direction, or away, that is in that direction, from the geographical position of the celestial body. Okay, or from the azimuth, the true bearing of the celestial body. Oh, okay, so by moving the line of position away, this is away, or towards, it's noted here, the direction of the celestial body, of the geographical position of the celestial body, this means along the azimuth, okay, by a certain distance, he could correct that error. Okay, what was that distance? That distance was equal to the error in minutes that he made to the altitude. Okay, and so this works because by definition we know that in our coordinate system 1 degree is 60 nautical miles, and so 1 mile equals 1 minute of latitude. Okay, voila. Now, small repetition. We all know what the geographical position is of a celestial body. We use the abbreviation GP. Okay, and when we draw a line between the celestial body and the center of the Earth, as you can see here, this is the center of the Earth, this is our celestial body. When we draw a line between the two, we see that where this line intersects with the surface of the Earth, that is what we call the geographical position. So it's the intersection of a line joining the celestial body and the inner surface of the Earth. Okay? Well, we all know already, because I've told you this already very often, that the geographical position of a celestial body is defined by two coordinates. We've looked them up, and you know now how to determine the geographical position of a celestial body for any time of the day, any time of the year. We find all this information in our nautical almanac, and you know that actually the geographical position is determined by one, declination, and secondly, the hour angle. When we start from Greenwich, we call it the Greenwich hour angle. That is what you can find in nautical almanac, but you know that when you apply, you add or subtract the longitude to the Greenwich hour angle that you get. We should all say this together, the local hour angle. Okay, and so it depends on whether your longitude is east or west, that you have to, if you have to subtract or add your longitude to your GHA in order to obtain the LHA. Okay, so you know that all these elements can be found in the nautical almanac on the daily pages, but a very important thing is, and that you already know as well already, you must know the exact time of observation. Otherwise, you don't know where to find or at what time to find the equatorial coordinates, because you know that these are the equatorial coordinates. Okay, otherwise you don't know at what time to find the equatorial coordinates of your celestial body in the nautical almanac. Okay, so here once again, declination is the elevation above the celestial equator. This is the celestial equator, and your GHA is the hour angle starting from the prime meridian, which is the Greenwich meridian. Okay, voilà. So, you know that Sumner found out that all ships sighting the sun at the same altitude, that they were all on one line. Okay. In practice, what do we see? We see that all observers sighting a celestial body at the same altitude, but in a different direction, they will stand on a circle of position with the geographical position of the celestial body that you're observing as a center. Okay, so what does this mean? If you have a celestial body, if you find the celestial body's geographical position on the Earth, what do you see? You see that all persons seeing the celestial body at the same altitude, this is altitude 1, this is altitude 2, but in a different direction, this is direction 1, this is direction 2, that they all find themselves on the same circle. Okay? And this circle is called the circle of equal altitude. Okay? This is the result on a flat surface. Okay? And so now I want to go back to this other drawing here. You see that, for example, when you have a celestial body, you find the geographical position. The geographical position is defined by the declination and the GHA. And then you see that all persons sighting this celestial body at an altitude, true altitude of 75 degrees, that they are all on a circle which is called the circle of equal altitude, which is this circle here. Okay, but then you can say, okay, but Sumner said he didn't talk about the circle. He said all ships sighting the sun at the same altitude as I observed with my sextant for different latitudes, they all are on the same line. What was that line? That line was this line of position, okay? This one that you see here, okay? So he sighted the sun at a certain direction. The direction was the azimuth. Oh, sorry, in this case, it's the other way around. Sorry, the azimuth is in that direction because this is your geographical position of a celestial body. And so all the ships sighting the celestial body at the same altitude and in the same direction, they must be somewhere here on this line of position. And this line of position, what is it? It's a tangent line, or it's a line tangential to the circle of equal altitude. Okay, voilà. And these are the lines of position that we will be using for our intercept method, okay, to determine our position during celestial observations. Okay, voilà. So if you see here a circle of equal altitude, this is our celestial body. Okay, we project it and we find the geographical position on Earth. Okay, this is your position. Okay, and then if we draw a circle, if we draw this circle of equal altitude, what do you see? You see that the radius of this circle, which is this one here, radius, you see here that the radius here is the distance between the position of the celestial body and your position. Okay, the distance between these two is called the zenith distance. Okay, and so now you can see that if you want to draw a circle of equal altitude, you know that the radius of the circle of equal altitude is equal to the zenith distance. Okay, now can we determine in practice the zenith distance? No, we cannot. But what can we determine? We can determine the altitude of the celestial body. Okay, and we know that if we subtract the altitude from 90 degrees, that we get the zenith distance. Okay, well, this is once again represented in another way. If this is your local horizon, okay, what can you do? You can determine the altitude of a celestial body. This is the altitude. 90 degrees minus the h, or altitude, is your zenith distance. Okay, if we transpose this to the center of the Earth, you see that this angle here is also the zenith distance, and it is equal to this arc that you see there. Okay, it's the arc between z and x, okay, which is actually the same one as the arc that you see there. This is the position of the celestial body. This is your position on Earth. We talked about this earlier. And the difference between the two is the zenithal distance. Okay, and then if we draw then a circle with the radius being the zenithal distance, we get this circle here, and that is then the equal altitude circle. Okay, altitude. Okay, so all persons standing somewhere on Earth on this equal altitude circle, they will all sight the celestial body at the same altitude. Okay, voilà. And this is again represented here. This is your celestial body. This is your position. Okay, this is your zenith. The difference between the two of them is the zenith distance. Okay, and then if we determine the celestial body's geographical position, we find the intersection between the line going from the celestial body to the center of the Earth. This is our geographical position. Okay, the geographical position is defined by the equatorial coordinates, being first the elevation above the celestial horizon, which is our declination. So we have first of all declination, and secondly, if this is the meridian of Greenwich measured in a westerly direction, we have the celestial body's Greenwich hour angle, which is this angle here. Okay, so as z, as you can see here, is our zenith distance, and it's also the radius of the equal altitude circle. Now, the only question that we still have to ask ourselves, where are we on the equal altitude circle? Are we somewhere here, or there, or whatever? Well, what comes into play then is we have to know what our azimuth is. Okay, and then if we know the azimuth, we know where this line intersects with the equal altitude circle, and that is where we can draw our line of position. Okay, our line of position being tangential to the circle of equal altitude. Okay, voila. So, in practice, what can we do? If we have the possibility to take 3 celestial observations, one here, one there, and one there, what can we do then? We can determine 3 different equal altitude circles, and then if we have done very good observations, in order to find our position, what can we do? We can find the intersection between these 3 altitude circles. In this case, it will be this point here, okay? And that will be then our true position. So if we take 2 or more observations, if we find the intersection between the altitude circles, we will find our true position. Okay, so we have 3 observations. This is observation 1, observation 2, and observation 3, with the 3 geographical positions of the celestial bodies. Then we can draw the equal altitude circles. How do we do this? We find the coordinates of the celestial bodies. This is again defined by the declination and the Greenwich hour angle. And then if we have an altitude, we can transform this into zenithal distance. 90 degrees minus the altitude is the zenithal distance. And so then we have the radius of our equal altitude circle. This is another zenith distance based on another elevation or altitude. This is zenith distance number 3. If we know the zenith distance, we can draw the equal altitude circle because we know the radius, and then the intersection between the 3 altitude circles is our true position. Okay, so indeed, if we would have a globe in our hands, it would be possible for us to measure the altitude of 3 stars. We would plot the geographical positions of these stars with our GHA and our declination. We would be able to determine the zenith distance because we've made observations with our sextant. We have measured the altitude. Okay. So we can determine the radius of the equal altitude circle. Then we would be able to draw the altitude circles on the globe, and the intersection, as you can see here, between the 3 altitude circles, that is our true position. Okay. But of course, we know that this is very impractical, and that there is a problem with this method, because in navigation we don't have the globe in our hands, and we do our navigation on charts that only represent a small fraction of the globe. So almost in all cases, even the geographical position won't even fit on our charts. Okay, so how do we go about it? We should be able actually to plot only a small part of the equal altitude circle. Okay, how can we do this? We can do this via the method Marc Saint-Hilaire invented a very long time ago. And so he found a solution to this problem, to the fact that we don't have the globe in our hands, okay? And to the fact that we can only plot a small segment of the equal altitude circle, okay? This method in Marc Saint-Hilaire invented is called the Intercept Method. And what is it based on? Well, he actually realized that when we do navigation, we always have some form of idea of where we are by doing dead reckoning. Okay, the position that we find there would be either our dead reckoning position or our estimated position. Okay, well, if we have an estimated position, what can we do? We can, instead of measuring the zenith distance from the geographical position of our celestial body, what can we do? We can also calculate via a formula based on our Navigational Triangle. We can calculate the estimated position. We can calculate the altitude of the body based on our estimated position. Okay, so what do we actually calculate? We calculate what we would expect the height to be, the height or the altitude of the celestial body to be, if we were actually in the estimated position. Okay, so we have our estimated position, And then we calculate via a formula based on the Navigational Triangle what our height would be if we were in the estimated position. Okay, how do we call this height or altitude? We call it HC, calculated altitude. Okay, as is mentioned here. Okay, so we first, on the one hand, calculate the altitude based on our estimated position, but secondly, we also have a sextant. So the second altitude that we get is from the actual observation that we do with our sextant, and that altitude we call HV. Okay, and if we compare then the calculated altitude based on the estimated position and the true altitude based on what we read on our sextant, if we compare these two, then we get the intercept. Okay, intercept is also called delta H. Delta always stands for difference, and so it means that the intercept is the difference between, how should I note it? It's the difference between HC and HV, and that is delta H. Okay, so maybe this should not be there, but delta H is the difference between HV and HC, as you can see here. Okay, voila. And so why is this called an intercept? If we take a look at the dictionary in English, we see that to intercept a curve or a line is to include a segment of it between 2 points or 2 lines. And what do we do in this case? We, along the azimuth, we intercept a segment between 2 points along the azimuth. And between which 2 points? Between our assumed or our estimated position, which is LE, GE, or our dead reckoning position, okay, along the azimuth line. And so we intercept between 2 points, okay, between the azimuth, estimated position and the point where we draw our line of position, okay. Voila. So what does this really mean in practice? In practice, we are at a certain estimated position or assumed position. We call it more often the estimated position, okay. And when we are on the estimated position, what do? Via our formula, we calculate the HC. That is the altitude that we would expect to see if we were actually at the estimated position. But in fact, we don't know whether we are in the estimated position or not. Okay, that is exactly what you are trying to calculate. We are trying to calculate where we exactly are. Okay, but if we are basing ourselves, or if we are starting from our estimated position and then calculate the height, what it would be, which is HC, and if we compare that to our observed height from our sextant, and we calculate then delta H, the difference between the true altitude and the corrected altitude, if we can calculate then delta H, we see that this will always be a difference, not in minutes, but not in degrees, but in, I don't know what, 2 minutes, 0.6 seconds, or 0.6 or something. And then we know that this can be transformed into a distance, okay? Because as I told you earlier, 1 degree is 60 miles. So here, 2 minutes, 0.6 equals 2.6 miles, nautical miles. Okay, so what can we do then? We can, starting from our estimated position, indicate the intercept, as you can see here. So we have our assumed or estimated position, and then starting from that position, we will either measure the intercept towards our geographical position or away from our geographical position. Okay, this depends on whether the intercept is positive or whether the intercept is negative. Okay, And then starting from our geographical or assumed position, we indicate the intercept. And let's say in this case, we have an intercept of 2.6, which is positive. We mark a distance of 2.6. This is the distance. And then where we end up, we can draw our line of position. This is the line of position. Okay. And what is the line of position? The line of position is nothing else than a line tangential to, this is our geographical position, when we have the observed or the true altitude. This is the true altitude that we measure from our sextant. If we then draw an equal altitude circle, okay, and we have a line which is tangential, I'll take a red one, tangential to this equal altitude circle, what do we have then? Then we find our line of position, okay, which is actually a small part representing the equal altitude circle. Okay, voila. Now I told you that sometimes the intercept is positive, sometimes it's negative. That depends on the I can't find the word, the verhouding, de rapport, of the verhouding between the true altitude and the calculated altitude. Okay, so you can see it here. If this is your celestial body, okay, here you find the geographical position of the celestial body. Okay, this is your estimated position, LE and GE. Okay, and so from the estimated position, you calculate here HC. Okay, but when what you read on your sextant is HV, in this case, HV is bigger than HC. You can see that from the angles here, these two angles. If HV is bigger than HC, it means that you're actually closer than what you have calculated. Okay, so you are closer to the geographical position than your estimated position. Okay, so that means that you will have to mark the intercept towards the position of the celestial body. Okay, so this means towards. Okay, so starting from your assumed position, what do you do? If you have a delta H of 1 minute, for example, you take 1 minute, you measure it starting from your geographical position, 1 minute, in the direction of your azimuth, okay, towards the celestial body. And there you find your line of position, okay? Voila. On the other hand, if again you have your celestial body and this is your geographical position, then this is your azimuth. Okay, this is the azimuth line. Okay, and you see that this here is your estimated position, LE and GE. Okay, HC is what you have calculated, but what you actually observe with your sextant is HV. Okay, you see here that HV is smaller than HC, so this means that you are further away from what you have calculated. Okay, so in this case, the intercept will be marked away from your estimated position. Okay, so again, if you have a delta H, which is the intercept, which is, let's say, 2 miles or 2 minutes, then you get an intercept that should be marked on the azimuth line, on the true bearing, away in the direction contrary to your true bearing. Okay, so it should be marked away. The distance is 2 miles, and then you find here your line of position. Okay, voila. So if you can't remember, for me it's difficult to remember things. I have a very, very bad brain, so or memory. I just try to find the answer by reasoning. Okay, in this, you know that when you are looking at something and when you're determining the height, if this is your celestial body, when you're close to the celestial body, your altitude will be h1. When you're far away from the celestial body, your altitude will be lower and it will be h2. Okay? So if you have, for example, I will mark this in green. If you have, for example, a calculated altitude, which is this one here, okay, and if your observation altitude h1 is bigger than what you have calculated, it means that you are closer. So this means that your intercept should be marked toward. If what you're actually citing or reading on your sextant is smaller, so if h2 is smaller than h3, you know that you are further away, so that the intercept should be marked away from. Okay, voilà. Now, you already know that on charts, we don't draw equal altitude circles, but the charts just aren't big enough. So what do? We draw tangents to the circles, okay? And these tangent lines, what are they called? They are called lines of position, okay? So actually, what do we have when this is a celestial body? This is the geographical position of the celestial body, okay? We have our calculated altitude coming from our estimated position, okay? And so if we compare this our sextant altitude, this is also a sextant altitude. If the true altitude is bigger, we see the celestial body under a larger angle, so this means that we are closer, okay? And so this means that the delta H is positive towards. If we are sighting the celestial body at an angle which is smaller, we know that we are further away and that delta H is in this case negative. Positive or negative, I don't care, you just have to understand whether you are closer or further away if you compare this to your calculated altitude. Okay, voila. And so what do we do? If we have a calculated altitude, what would we have? I'll erase this a little bit. What would we have? We would actually be on, if this is the celestial body, we would actually be on an equal altitude circle based on our HC and the zenith distance that corresponds to HC. Okay, let's say that our altitude that we observe with the sextant is bigger. That means that we are on this equal altitude circle, okay, with the zenith distance based on HV. Okay, the difference between these two is delta H, and that can be considered as our intercept. Okay, so starting from our estimation, we draw our azimuth. Okay, in this case it will be in this direction, and then we determine whether we have to mark the intercept towards or away from the celestial body. And then if we indicate the point of the value of the intercept on this on our, but I'll take another color, it's a little confusing. If we indicate the intercept on our azimuth line, then there we can determine what our line of position, or where our line of position will be. Okay, voila. So you know the question asked here, at which of the circle do we draw the tangent line? I've already answered this question to you. We draw this tangent line at a point where, what was it again? The point where the azimuth line intersects with the true altitude circle. Okay, so at this point we draw our line of position. Okay, voila. So on a chart, we know that we are somewhere on the equal altitude circle. if we would have a very big chart, but we still need to determine, excuse me, in which direction we are. So we need to determine in which direction we see the celestial body, and this is determined by the azimuth angle or the true bearing of the celestial body. Okay, so what do we have in practice? We have our geographical position. We can draw a circle of equal altitude because we have our true altitude. 90 degrees minus the true altitude is our zenith distance. This will allow us to draw the equal altitude circle. And now we need to determine whether we are here or there or here. Okay, so what we do? We determine our bearing. Okay, and so we have our estimated position, and starting from the estimated position, we determine our true bearing, which is this one here, and where the true bearing intersects with the equal altitude circle, that is where we draw our line of position. Okay, voilà. And so in practice, this part here, what does it represent? From the estimated position, we have our calculated altitude. Okay, then we have our here our true altitude. Okay, and so we know that our delta H in this case will be positive. Okay, towards that we mark on our on our azimuth line, on our bearing, and where that point then intersects, we can draw the line of position. Okay, so that's actually what Marc Saint-Hilaire is based on. He only cares about this. He doesn't draw the equal altitude circle because in practice that's impossible, as I told you. So Marc Saint-Hilaire works the other way around. He starts from his, I will erase all this and start all over again. So what does Marc Saint-Hilaire do? He says, okay, what I've drawn earlier, he says, okay, it's impossible to draw this equal altitude circle because our charts aren't big enough. So what do? We start from our estimated position. There we calculate the calculated altitude. We also see what our sextant says. From our sextant, if we correct the sextant height, we get the true altitude. We compare the true altitude with the calculated altitude. This gives us a delta H, and this is our intercept. And so, as I told you, in this case, we know that the intercept is positive towards, and so at that point, we don't have this circle, but at that point, we draw our line of position. Okay? So, and then if we have two observations, what could we do if we would have very big charts? We could determine the zenith distance for the two observations, okay, which is 90 degrees again, minus the altitude. We could then draw the equal altitude circles. This is circle 1, this is circle 2, okay, and where they intersect, that is our position, okay. But what could we also do? We could say, okay, we know our estimated position. This is our estimated position. This gives us an HC for both HC1 and HC2 for both celestial bodies. Okay. Then we compare this with our true altitude based on what we read on our sextant. We determine 2 times the intercept. Okay. And then we mark the intercept 1 and intercept number 2 on our true bearing. And if we have marked the intercept, what do we find? We find line of position 1 and 2, and where they intersect, again, that is what our true position will be. Okay, and so it's this second system that we will be using. Okay, voila. So again, this is the same thing. We have a geographical position for X, for dead reckoning latitudes. Okay, so based on our dead reckoning latitude, we will have this first circle of equal altitude in our minds based on what? On our HC. Okay, Then we also have a true altitude based on what we see with our sextant. Excuse me. This gives us equal altitude circle number 2. And the difference between the two of them, that is called our delta H. Okay. And so we have here again also the second, sorry, in this case, this is our second equal altitude. This is the second equal altitude circle. So, and where they intersect, that is where the two lines of position intersect. That is our that is our true position. Sorry, allez. That is then our true position. Okay, it's the intersection between two equal altitude circles, the green ones, but also the intersection between the two lines of position. Okay, which are these two. Okay, and they intersect at the same point. Okay, so again, we have 3 equal altitude circles. And for each equal altitude circle, we have observations, altitudes. If we are able to calculate, to draw the altitude circles, we find our position. But in practice, we will not be able to draw the circles. We will only be able to draw the lines tangential to the equal altitude circles, and they will give us our true position. Okay. Voilà. So again, I keep repeating myself in order to try to make it clear to you. Geographical position, assumed position. The assumed position gives you the computed altitude circle, which is, I'll use the same color, the red one in this case. Then we mark the intercept. This is the intercept. We find the altitude circle based on our sextant reading. Okay, but in practice, we are unable to draw these circles. So, starting from our assumed position, in this case, away from this is our true bearing. But we will have to mark the intercept now away from our true bearing. Because, why? Because our calculated altitude is bigger than our true altitude. Okay, and this is what you can see here. Okay, HC is bigger than HV. So we have to mark the intercept away from our dead reckoning position. Okay, voilà. So in this case, what do you think? If this is our geographical position, and this is the position of the calculated altitude circle. Okay, calculated altitude is based on our estimated position. So is the intercept positive or negative? In this case, the intercept will be towards. So it will be positive. Okay. So intercept method, a small recap. So we start from our dead reckoning or estimated position, which is the best guess of our position. And using the dead reckoning position, we calculate the expected altitude for a star at a given time at that position. This is called HC, based on estimated lat and long. And then we compare HC to what we read on our sextant. And the result here is the intercept. Okay, and this intercept is marked on the true bearing in order to find our line of position. Okay, voilà. So I think this is something that you should understand now already. We have an assumed position. We mark an intercept towards, so our intercept is positive. If this is our true position, this is away, because this is the direction to our geographical position of our star. If we mark it away, we know that delta H is negative. Okay, and in both cases, what we end up with is this line of position. Okay, voilà. Now, I already told you a couple of times that based on the estimated position, we can calculate with a formula our calculated altitude. Okay, this formula results from the navigational triangle that we've already used a couple of times. Okay, if you use the rule of cosine, we know that the cosine of z is the cosine of the polar distance multiplied by the cosine of col plus the sine of polar distance multiplied by the sine of col multiplied by the cosine of p. Okay, this gives us then, if we transform this into this formula here, we know that 90 degrees minus zenith distance is hc, etc., etc. So we know that the cosine of z is the sine of hc. Col becomes LE, polar distance becomes declination, because we know if this is our polar distance, we know that this is our declination. Okay, col becomes LE if we change cosine to sine, and so this way we can end up with this formula here. And this is the basic formula in order to calculate our calculated altitude. So here again the same thing, polar distance becomes declination, col becomes L, and so P remains the same. Okay, our latitude that we use in this formula, you know that HC is based on LE and GE, so the latitude that we use is the estimated latitude, as you can see here. Okay, the other elements are the polar angle and the declination. Okay, declination we find in the nautical almanac. And how do we find the polar angle? The polar angle, what is it? We know that we have the GHA from our we calculate the GHA from whatever, let's say the sun or a star or whatever. We have the GHA of the celestial body. We end up with that one way or another. I explained that to you in an earlier recording. Then what do? We add or subtract the longitude in order to get the local hour angle, and then the local hour angle we transform into P. If LHA is bigger than 180, we know that the polar angle is east. If LHA is smaller than 180 degrees, we know that polar angle is west. And if LHA is bigger than 180 degrees, polar angle is 360 minus LHA. But these are things that you should all know by now. Okay. Well, now in this formula, we need to define whether we have to add or subtract there, because in some cases, when latitude and declination have a different name, declination should be treated as a negative value. Okay, when declination and latitude are the same, declination is treated as a positive value, so you should add. When declination and latitude have a different name, declination is treated as a negative value, so you should subtract. Okay, so that is what you see there. Our formula becomes this one here. So the signage of HC is the cosinus of col, cosinus declination, cosinus P, and then plus or minus the sine of L multiplied by the sine of the declination. And you have to add when latitude and declination have the same name, and subtract when latitude and declination have a different name. Okay, so this comes from what you see here. Latitude and declination have the same name, then the declination is treated as a positive value. Declination is always smaller than 90 degrees. It goes from 0 to 90 degrees to the north, up to 90 degrees to the south, or it can go from and then if the declination is treated as a positive value, you know when the angle is between 0 and 90 degrees that this will always be positive, so you will have to add. Okay, if latitude and declination have a different name, declination should be treated as a negative value. So if you fill this out in this formula there, you see that the sinus of negative value is negative, so, and the cosine of a negative angle is also always positive. Okay, so here you see that you need to subtract this value from this value here. Okay, this is only and alone to do with cosine. You know that if this is 1, the cosine should be measured here. So if you have a positive value or a negative value, cosine is always positive between 0 and 1. But if you take a look at the sinus, if you're between 0 and 90 degrees, the sinus will be positive, but when you have a negative value for the declination, your sinus will be negative. Okay, this is where you read the sinus, this is where you read the cosine. Okay, and that is what is behind this reasoning here. Okay, so voila, this is our navigational triangle here. And if we take a look at this navigation triangle, what do we actually know? We have our estimated latitude, so we know our co-latitude, so this side is known. We know our declination that we get from the nautical almanac, so we know the polar distance. And we also know the GHA or LHA, so we can determine the polar angle. Okay. So what can we do? We can also calculate our zenith distance, because we have from our observation H3, and voila. If we calculate HC, we also know the zenith distance, which is the height that we would expect the body to be, the celestial body to have if we were in the dead reckoning position. Okay, so if we use this reasoning, we know that we know all the elements from the navigational triangle in order to solve this formula, the one that you see here. Okay, voilà. And so the formula is the sinus of HC is cosine declination multiplied by the cosine of LE multiplied by the cosine of P, plus or minus the sinus of the declination multiplied by the sinus of estimated latitude. Okay, being the one that we use here. Okay, that's more practical because the minus will be introduced via the sinus of the declination there when latitude and declination have different names. Okay, voila. And so if we then have our calculated altitude, we compare this what we read on our sextant, this gives us delta H, okay, which will be either towards or away from. Okay, voila. So this is an example on how to calculate the intercept method. The basic is that we will calculate HV and HE in order to get delta H, but I'll do a practical exercise with you later on. Okay. So what do we do in practice? We take the sextant height of a chosen celestial body and add our corrections. This gives us HV. We note the exact time of observation. We determine our dead reckoning position. We can then determine the geographical position of the celestial body using the nautical almanac. We can determine GHA and declination. We turn this into polar angle, and then we can calculate HC with our formula. Okay. If we compare this then to what we have read on our sextant, this gives us HV. If we compare these two values, this will give us the intercept. And then the last thing to do is to calculate the bearing or the azimuth of the celestial body, because then we will know where, in which direction, away or towards, along the azimuth line, we will have to mark the intercept. And then if we find the intercept, we will find the line. We will know where to position the line of position. Okay, so voila. Now, let's do an exercise. I'll try to find my calculations. So we have an estimated position, which can be our dead reckoning position or estimated position. The position is 31 degrees, 41.4 south, and 104 degrees, 51.7 east. Okay, we are on the 26th of August 2020. Our watch time is 5:29. Our chrono time and our chrono correction is given. We also know the height of the eye and our index correction. This is altitude corrections. I have included a recording on this. I've publicized it on Blackboard, but this is what we have saw in the first year. Okay, what we have seen, sorry, in the first year. And so we do an observation of Aldebaran, which is a star, and our instrument height says 40 degrees, 31.5. Okay, so then we start filling out this form here. We do an observation of Aldebaran. The date is the 26th of August, 2020. Okay, our watch time is 5:28. Sorry, 29. And so we know that we also know our chronometer time. Our chronometer time is 10:32:33. So what do we need to do? We need to determine whether our chronometer time is AM or PM. How do we do this? We take our longitude and we transform this into time. Okay, so we do this via the conversion of arc to time. Okay, this gives us for the 104 degrees, this gives us 656 plus 327. So we have 06:59:27. Okay. We need to do something with this. We apply this on our watch time. 06:59:27. Okay. Our longitude is east, so we are in the east. This is Greenwich. This is where we are. This is our estimated position. So here it is later. So in this case, what do we need to do? We need to subtract in order to get approximate GMT. Okay. So this gives us then, if I'm not mistaken, 22, 29, 33. And then we are one day earlier. We are on the 25th. Okay. So we know now that our chronometer time is PM. Okay, so we need to actually add 12 hours. So this will become 22, 32, 33. Okay, there is a correction in your chronometer that you know it's minus 2 minutes. So we have now a universal time of 22, 30, 32. Okay, now the first thing to do is to determine our geographical position. So we need to determine the GHA and declination in order to get our polar angle. That are the elements that we need to calculate HC. Okay, because the formula is the sinus of HC is cosinus latitude, cosinus declination, cosinus P, plus or minus sinus latitude, sinus declination. Okay, our latitude that we know our estimated position. The declination we get from the nautical almanac. Okay, and the polar angle we calculate with our GHA and our declination. So first, we are calculating the GHA for a star. So we start from the GHA for Aries. If you take a look in the nautical almanac, you will see that this is 304, 37.2. We have to add increments because this is the observation at 2200, but we need to add increments for our 30 minutes, 33 seconds. The increments correspond to 7 degrees, 39.5. Okay, I advise you to take the nautical almanac by hand and to do this exercise together with me. Okay, increments are always to be added, so this gives you a GHA of 312 degrees, 16.7. Okay, then in the nautical almanac you also find the SHA, because you know that the GHA of your star is starting from the GHA of Aries, and then you add the sidereal hour angle. In this case, the SHA is what you see here. That is always also to be added. Okay, if this is more than 360 degrees, you subtract 360 degrees, and this will give you then 242 59.4. Okay, this is our GHA for the star, but we want our local hour angle for the star. So what do? We have to do something with our longitude, 51.7. Our longitude was east, so Greenwich is least, so in this case we have to add, okay, and this will give you then 1,374.51. Okay, this value is bigger than 180 degrees, so my polar angle is east, that I already know, and it is equal to 360 minus the local hour angle. Okay, so my polar angle is 12 degrees 08.9. Okay, we forgot to note our declination. The declination of a star here, it is north, it's indicated next to the SHA, 16 degrees 33.0. There is no correction. Okay, so now I have determined my polar angle and my declination. So in fact, now I can already calculate my HC. Okay, if you calculate this, you will see that HC is, the sinus of HC is, first this part here, this part will correspond to, I will write the intermediate values as well, minus this part here, that is equal to 96. Okay, we have to subtract in this case because our latitude is south, our declination is north, so they have a different name, so we have to subtract. Okay, because now declination is treated as a negative value, and so the sinus of a negative angle is negative, so this becomes a minus. Okay, so this gives us then 0.6477, and this corresponds to a calculated altitude of 40 degrees 22.18. Okay, voilà. Then, so we have our polar angle. In order to make our drawing, we need to know where, in what direction, we need to mark our intercept. Okay, so for the intercept, for the azimuth, sorry, we will need to calculate with the ABC tables. The values for ABC, the value for A is 2.87. Named opposite to latitude, except when our angle is between 90 and 270, so this is not the case. Then the value for B is 141, same name as declination. So we have to add these two values, and this gives us then 428 north. Okay, then we go into the C tables, and in these C tables we find azimuth, which is north and east. North coming from C and east from our polar angle. Okay, and so we have 15 degrees 0.3. Okay, so this means that our true bearing is also 15 degrees 0.3. Okay, now the only thing that we need now is our true altitude. Then we can calculate our delta H. Okay, the instrument height that we read from our sextant, we've done this last year, we've done exercises on this, is 40 degrees 31.5. The first thing to do is to mark the index correction, which is minus 01.0, so this gives us 30.5. Then we need to correct for the height of the eye. This is called the dip correction. Our height of the eye is 10 meters, if I'm not mistaken. So it's given here in this exercise. So this gives us a dip correction, which is always negative, of minus 5.6. And this gives you then an apparent altitude of 40 degrees, 24.9. Okay. Then we need to add a correction for the main correction for refraction. In this case, this is minus 1.1. We are in standard atmospherical conditions, so there is no further correction. And this gives us then an HV of 40 degrees, 23.8. 40 degrees, 23.8. If we compare this to our calculated altitude, we see that we have a difference. This is 0.3. We see that we have a difference of 1.5. And our true altitude is bigger than our calculated altitude. So this means that we are closer to the geographical position than we have calculated with our estimated position. So this means that our delta H is positive. Okay, let me make this drawing once again. If this is your geographical position, this is the star. In this case, it's a flower. This is the geographical position. This is our direction of our true bearing. And this is our estimated altitude, estimated position. And we find here our calculated altitude, but we have seen that our true altitude is bigger. So we know that the intercept in this case, wait, this is the intercept. The intercept is in this case positive, so this means towards the geographical position in the direction of our true bearing. Okay, voila. And so this is how we will calculate our intercepts. Okay, so I'll try to show this is again an explanation on the altitude corrections, but this is what we have done last year. So this is now we have calculated the delta H and the line of position for one celestial body, but in practice what will we do? We will need to make a combination of at least 2 or better even 3 celestial observations in order to get a fix. Okay, so and on this drawing here, what do you see? You start from your, here, I'll erase this. You start here from your assumed position. Okay, and then from the assumed position, you have bearings. Okay, this is bearing number 1, bearing number 2, and bearing number 3. Okay, and so on these bearings, what do you indicate? You have to indicate the intercepts. Okay, intercept 1, intercept 2, intercept 3. Okay, this intercept is positive towards, this intercept is also positive, and this one also. All three intercepts are positive. Okay, and so then we can draw the lines of position. Okay, I'll take a red color for that. These are the lines of position, perpendicular, very important, always perpendicular to the true bearings marked at the end position of your intercept. Okay, so you have a line of position 1, line of position 2, line of position 3. Okay, and then you find that they don't intersect at one point. We have this area, this green triangle actually. Okay, this green triangle, we'll talk about that later on, but this green triangle is called the cocked hat. And what do we actually do in practice? We try to determine the center point of this cocked hat, of this position triangle, and that is then where we find our true position. Okay, so this is what we will do in practice. We combine 2 or more lines of position in order to get a triangle, or maybe even, this is what they call, if we only have 2 observations, we get a fix. If you have 2 observations, you get this. If you get 3 observations, you get this triangle, and then this will be your 6, that's the position 6, okay, with line of position 1, line of position 2, line of position 3. The line of position is always perpendicular to the 2 bare, and it is marked away or towards. Okay, voilà. Now I'll take a short break here, and we'll continue later on with possible errors in lines of position. Good luck.